Hello everyone, I'm Aditya Tandon, and I work at the Institute of Digital and Autonomous Construction at the Hamburg University of Technology. Today I'll present our work on automating building inspections by combining building information modeling and behavior trees. The primary motivation is how do we effectively inspect buildings. Most civil infrastructure requires to be inspected regularly to ensure it can be operated safely. Most of the inspections even today are completely manual in nature, and the problem with manual inspections is that they can either be hazardous in certain regions, they can also be extremely labor intensive and dependent on skilled labor, and the largest problem is that they can be extremely subjective. What we propose is that mobile robots can be utilized to automate building inspections and also to standardize them. But what really prevents robots from being used today to automate building inspections? Number one, most robots still do not utilize semantic and geometric information from building information models, and none of the task and motion planning algorithms for these robots are actually informed by these processes. A bigger thing is that robots, so the real world is actually messy, and robots struggle with being adaptable and to dynamically replan in these environments. And what we also found is that most prior work in this direction was limited to simulation environments. So what we want to do is actually leverage the geometric and semantic information that's available in BIM models to guide robotic inspection missions. So what we're trying to do is integrate BIM software directly with robotic software. And we propose then deploying behavior trees to make the robotic inspection more adaptable and robust in the face of changes between the real, so the as-built state and the as-planned state. Our framework looks at three major modules. The first one is using BIM models and generating tasks from the BIM models itself. Robots still utilize maps that are specific to robot navigation. So in this case, we're still talking about 2D occupancy grid maps. And what we try to do is align the BIM models with these robot navigation maps. So any task that we create using the BIM models can directly be made available on the robot navigation maps. To actually perform the inspection, we model the capabilities of a robot using behavior trees. And these behavior trees can then be used for task execution on the robot navigation map. So essentially, this framework then allows us to generate tasks from the BIM models and execute them reliably with robot behaviors models as capabilities. To look at the first component, we actually take a BIM model and we extract the relevant building elements. So in this case, we look at certain building elements of type T, which are electrical sockets or electrical outlets. And we then calculate the inspection poses that are required to actually perform this inspection. So in this case, we are limiting ourselves to visual inspections. And we calculate the inspection poses P that are required based on the position, based on the pose of the element from the BIM model. This is determined using a predetermined homogeneous transformation, which is then suitable for the type of building element that needs to be inspected. The second component of the framework focuses on aligning these BIM models with robot navigation maps. So to do this, we use fiducial markers. In our case, we're using April tags. And the way we do this is we actually place April tags at corresponding locations between the BIM model and the actual real world. What we are trying to determine here is this transformation, BTM, that allows the alignment of the robot navigation map with the BIM model frame. To do this, we now calculate the other transformations. So the robot frame R and the map frame M are already related with one another by the transformation MTR at time t. This is known through the internal localization system of the robot. We also know the transformation BTA, which relates the BIM model to the April tag frame, since we've placed the April tags at the corresponding location. And when the camera of the robot is activated and observes the April tag, we then determine the transformation RTA. This allows us to complete the transformation chain and then determine the transform to align the robot navigation map with the BIM models. So essentially, allowing the calculation of BTM. The last part deals with expressing robot capabilities in the form of subtrees. And the way this is done, so as an example here, what we use is the navigation subtree. As the navigation subtree is ticked, the robot checks whether it receives the goal or not. As the goal is received, it checks whether the robot is already at the goal position or not. So when we say, yeah, the robot is not at the goal position, we can now plan our path in the environment, and then pass this on to a module that oversees the movement or the motion planning of the robot. And when this is executed successfully, the ticking of the tree actually ends. In case it fails, we have a navigation recovery option that allows recovery behaviors to be executed to allow for reliable task execution. Another example of a behavior tree that we use here is actually the visual inspection subtree. What we say is that when the robot is at the inspection location, ideally the robot will then want to check whether the camera is available or is on. In case not, we have options to relaunch the camera or launch the camera in the first place. And then check whether the object detector, to check whether the element that it's supposed to inspect is actually visible or not. In case that is not visible, the object detection module can again be relaunched. When everything goes well, we can capture the image. And in case something here fails, we then move to the visual inspection recovery mechanism. To implement this, we implemented the whole framework in Python and with the robot operating system. We extracted building elements and calculated the inspection poses using IFC OpenShell, and utilized the April tag ROS library for detecting April tags, and the SciPy library for optimization between the BIM alignment with the map frame. Lastly, the robot capabilities with behavior trees was developed using the ROS BDPy framework, but we extended this framework heavily to allow custom behaviors and capabilities to be modeled and then implemented. We then validated our framework in a real-world environment. So what we have here is actually an indoor office environment with multiple electrical outlets and April tags that have been placed at corresponding locations. And we wanted to primarily validate, number one, the accuracy of the inspection framework and also the reliability of the inspection framework. So to validate the accuracy of the inspection framework, we plan an inspection mission. What you can see here are the inspection poses that have been calculated based on an alignment between the BIM model and the robot navigation map. And this is then executed in the form of an overall inspection mission. What you see from the image on the left is actually the element that we want to inspect. And what we do is we fix an inspection pose marker, which is calculated at a 1 meter distance from the building element that needs to be inspected. And this inspection mission is then run 3 times, so for all 5 poses. And what you see here are actually values in meters, which are deviations between the actual robot position and the inspection pose marker. We have an overall root mean square error in 2D only of about 13 centimeters, which we deem to be satisfactory for the case of visual inspections. To validate the reliability of the inspection framework, we create an inspection mission by chaining the different subtrees in an overall behavior tree. And as you can see here from one of the inspection missions that we carried out, at the first stage, the BIM model is then aligned when an April tag is seen. Once the BIM model is aligned with the robot navigation frame, we now calculate these 5 different inspection poses, which are directly facing our building elements that need to be inspected. The path, so here you see the robot is already navigated from the first waypoint to, from its start position to the first waypoint. And now the robot, once it's done visually inspecting the target building element, it then plans its path and moves on to the second waypoint. What can be seen here at the second waypoint is that everything runs well. But as we now move to the third inspection waypoint, that's where the value of the framework really comes out, because the robot navigation map here is actually incomplete. So the path that's been planned is not optimal. The navigation recovery behavior is then executed, giving the robot time to replan. And as the robot moves around, you can see that the robot is now successfully replanned without stopping in the middle or aborting the inspection mission. So what can be seen here is that as certain modules become unavailable, or as certain modules fail to adapt to real-world environments. This framework that utilizes behavior trees actually allows robust execution in these regions where there could be significant deviations between the as-built state and the as-planned state in the BIM model. What you see here is the the navigation of the robot to the last navigation waypoint, where it now inspects the last building element. So here is an example of the images that were actually captured during the visual inspection. As you can see, the socket was identified and was then captured during the complete inspection mission. To summarize our work, we find a way to enhance our task and motion planning algorithms by leveraging BIM data, and we find a way to reliably perform inspections in real-world conditions, which actually is still messy. And we actually realized that we were able to successfully execute all of this. In future work, we look to extend this framework for different building elements and different inspection types, and also along with multiple robots. And what we also want to explore is how these BIM models can be aligned with robot navigation maps without actually modifying the environment, so without actually adding April tags in the environment. And that's all. So thank you so much.